All right, this is going to be a review of every topic on the AP Physics C Mechanics exam. The first topic is kinematics. So if the AP be giving you a position as a function of time, guess what? You're probably going to take a derivative of it because the derivative of the position equals the velocity. So if I take a derivative of this, I'd get 6t squared minus 6. That would be my velocity function right here. And if you take a derivative of the velocity function, you get the acceleration. So if the AP be throwing you a velocity as a function of time, take a derivative of it, that would get you your acceleration over here. You can keep taking derivatives that give you the jerk, the snap, the crackle, the pop, so on, lock and drop, but you probably don't want to do that. If the AP be giving you an acceleration as a function of time, you're probably going to integrate it because the integral of acceleration is going to be the change in velocity. You know, if you just separate this differential equation over here and you integrate, you'll get this. It's the change in velocity though. Be careful. It's not the velocity. It's the difference in velocity between a limit 1 and limit 2, whatever those are. And so if I integrate both sides here, I integrate my acceleration dt, I'm going to get 12 t squared over 2, that's just 6t squared plus a constant. What's that constant? That constant would be the initial velocity, which for our case was -6. So you'd have to be given that information. You can't just figure it out without knowing that beforehand. What do you do if you have a velocity graph? I said you take a derivative to get the acceleration, but you could also take an integral, integrate the velocity graph to get the change in position, how far that thing went. So if I integrate this with respect to time, I'm going to get 6t cubed over 3 minus 6t plus a constant. That's just going to be my position as a function of time. So, I mean, there's a geometric interpretation. The derivative of the position is just the slope. So the slope of the position graph equals the velocity. The slope of the velocity graph equals the acceleration. The area underneath the acceleration graph equals the change in velocity, and the area underneath the velocity graph is the change in position. So, you know, you can do this for any function. If you get acceleration, velocity, or position as a function of time, you can integrate, take a derivative if you want. What's the verb of derivative? No, derivative. Take a derivative and you get your values. What if the velocity is constant? This one's easy. I mean, this is about the easiest formula you can get. If the velocity is constant, distance equals rate times time. Do you ever have to use, can you ever use such an easy formula on the AP Physics C exam? Yeah, if you got a 2D kinematics problem, something flies off a cliff like that, in the horizontal direction, there's no acceleration in the horizontal direction. Because gravity just be pulling down. Gravity doesn't pull right or left. That means the distance in the x direction just equals velocity x times t. Whatever that velocity was in the x direction stays the same the whole way, so you could be using that. What if acceleration, what if velocity is not constant, but what if acceleration is constant? Then you can use the kinematic formulas. I mean, you could derive these using calculus, but they're given to you on the formula sheet if you need them. This you'd have to use for the y direction, because in the y direction, the velocity keeps on changing. So these are all for the y direction if you want. You know, acceleration in the y direction is always negative 9.8, but you could typically treat that as just negative 10 if you want to find a value. What if the acceleration is not constant? Well, okay, then you got to use some calculus here, do something. Sometimes you use conservation of energy to get your value. Maybe you can use conservation of momentum, or you just straight up derive it from Newton's second law and knowing what you need to do. What is Newton's second law? Well, it's this one right here. It's the fact that the acceleration is going to equal the net force per mass divided by the mass, the inertia of the system. You know, you can do simple problems on this, or you could do some harder ones. The one that the AP likes to do is air resistance. So air resistance is typically negative some constant times the velocity, or the velocity squared if you want to represent it in that way. But oftentimes it's just velocity. What do I do with this? Well, you can throw it in here. So let's say we had some car with a mass m, and it's coasting to a stop. So it's not pushing on the gas. You got your gravity, you got your normal force. Those are just going to balance. But you got this resistive force backward that's going to slow this car down to a stop. I mean, the graph's going to look like this. It started with some speed, and it's going to slow down to a stop like that. How would you get this function, velocity as a function of time? You'd use this formula here. You'd say that the acceleration would be negative bv. That's the force backward, and it's in the opposite direction of v. That's what's important. It doesn't matter if it points left or right here. The negative here doesn't mean left. It means opposite direction of v. So if this car is moving right, negative right is left. If this car is moving left, negative left is right. So you always need that negative there, even if the car was going to the left. You divide by m. This is a function of v. This isn't constant. I can't plug this into a kinematic formula. V is not a constant here. What do? I turn this into a differential equation. How do I do that? I write A as dv dt. So I'm going to write A as dv dt. How do I know to write it as dv dt? Because my force is a function of V. So I'm going to do equals negative bv over m. Now I need to separate this equation. I got V and T are my variables, and I got a V over here. B and M are constants. B and M can go anywhere. I need all the V's on one side, all the T's on the other. So I'm going to divide both sides by V, and then I'm going to multiply both sides by dt. So I'll get negative B over M dt. I've separated, so separate. Then I integrate from 0 to T. I'm going to assume I start my clock at 0. From V initial, not from 0. This car had some initial speed, whatever it was, to V. I integrate both sides. On the left-hand side, I get a log, a natural log. So I get natural log of V minus natural log of V naught equals negative B over M. On the right-hand side, I just get T from 0 to T. And then I'm going to write this difference of logs as the log of the ratio, V over V naught, going to equal negative B over MT. I'm going to take e to the both sides because that gets rid of my log. So e cancels that. I get e to the that. I'm going to bring it back up here. Sorry, a little messy. I'm going to get V over V naught equals e to the negative B over MT. I solve this for V. That V that I'm getting is V as a function of time, and it is going to be V naught e to the negative B over M times time. That's why this is a negative exponential. It dies off like e to the negative. What if I was falling through the air? Now I've got another force here, gravity, mg. How do I do it? I do it the same way. I plug in up here, but I'm going to have dv dt. dv dt. Now I have two forces here. I'm going to treat down as positive because treating the direction of motion as positive typically makes things easier. So down's going to be positive, mg, minus bv. Notice I'm still putting the minus here. It points up. Why? Well, I'm calling down positive, but that doesn't matter. Opposite the direction of the velocity. Even if I called up positive, I'd want to call this negative bv. So just be careful there. It's always got to be negative because it's opposite direction of velocity. Divide by m. I just do the same move. I separate, I integrate, and then I forgot to celebrate. Integrate, separate, integrate, celebrate. I celebrate. I got my answer right over here. So here, we got to separate. First step, dv divided by, I have to move this whole thing. These guys move as a family. If you try to separate these, it's bad. Don't separate families. What are you, a monster? Take this thing, family moves together over here, mg minus bv equals dt over m. You separate these guys, you are never getting this thing to fully separate here. Now all my v's are on one side, my t's are on the other. I'm going to integrate. From 0 to t. This time, let's say this guy started at rest, v initial 0. So I'm going to integrate from 0 to v naught. Oh, not to v naught, to v final. This is the v final at this time t. Left-hand side is going to give me, well, I do u, like u substitution, 1 over negative b if you do that, log of mg minus bv on the left equals, and then I get t over m on the right. And be careful, from 0 to v, and you might be like, oh, but the zero limit yields 0. No, it doesn't. You're going to plug 0 into v. You are not going to get 0. So be careful. You're going to get negative 1. Let's just move this negative 1 over b over. It's not going to hurt anybody. Let's move this over. Get it out of the way. So negative 1 over b is going to go over to the right. I'm going to plug these in here. I'm going to get log of mg minus bv minus log of just mg, because I'm plugging in 0 for my v. The 0 limit did not give 0. Be careful there. Equals, I move my negative b over. I'm getting negative b over m times t. All right, I'm going to write this difference of logs as the ratio of logs. I'm going to solve. Boring algebra. I'm going to end up getting that v as a function of time. Try it on your own if you want. Is going to be, I guess it's mg over b times 1 minus e to the negative b over m times t. This is going to look like this. Starts at 0. At t equals 0, 1 minus 1 is going to give 0. And it builds up to some asymptote. What is this asymptote? It's the terminal velocity. That's the fastest you're going to get. So at some point, this air resistance equals the force of gravity, and at that point, you stop speeding up. You don't stop. You just continue on with the constant velocity. This is that constant velocity. It's called the terminal velocity. You can get it easier. Just ask, hey, when will this equal 0? What equals 0 when mg equals bv, i.e. when mg over b equals vt. So that's solve for this velocity here, and it just gives you what the terminal velocity is without having to go through all this mess right here. So that's differential equations. Separate, integrate, celebrate. Sometimes there's seemingly easier force problems. You're like, oh, this one's easy. There's no differential equations here. Yeah, but it's not necessarily easy. You got a 4 kilogram mass on top of a 6 kilogram mass. And there's enough friction here that they just move together, right? They don't slip right there, but it's frictionless on this floor right here. So you're going to pull on the 4 kilogram mass with 20 newtons, and this whole thing's going to slide to the right. And I want to find what's the force on the 4 kilogram mass exerted by the 6 kilogram mass. What do I do? There's all kinds of masses. Like, what mass do I plug in? You got to keep this straight. You got to make sure you're always talking about the same thing. You can't be plugging in acceleration of the 6 kilogram mass, force on the 4, mass of the 10. You have to be acceleration of 6, force on 6, mass on 6. But the first thing we're going to do, since these slide together, anytime two masses accelerate at the same rate, you can treat them as one big mass. So I'm just going to treat this as acceleration of the whole thing equals net force on the whole thing over mass of the whole thing. I'm just going to be like, well, okay, fine. The force on the whole thing is just 20. There's no other external forces. Like, there's normal and gravity, but those balance out. There's no other horizontal forces. There's internal forces, but those aren't going to affect the acceleration of the whole system. Only external forces affect the acceleration of the whole system. 20 newtons is the net external force over 10 kilograms is the mass. That gives me 2 meters per second squared. This is useful because this is the acceleration of both of these masses. Now I can focus on either one. You'd be like, which one do I? It doesn't matter. You can focus on either one. Actually, we could do the 4. Let's do the 4. So the 4 is going to have an acceleration of 2. We know that. 2 meters per second squared. I'm using Newton's second law. Equals, so I got 20 to the right, minus whatever that force is exerted by the 6 on the 4, and that's going to go leftward. The 6 is going to exert a force on the 4 to the left. If you don't believe me, I'll prove it to you in a minute. Divided by, well, the mass is 4 kilograms. So 4 kilograms. I solve this for F. I'm going to get 8 over here equals 20 minus F. F, in other words, is going to be 12 newtons. That's the force on the 4 by the 6. What if I had picked the 6? Same thing. I could just be like, okay, fine. 2 meters per second. That's squared, sorry. That's going to be the acceleration of the 6 because everything's accelerating at the same rate. Equals, well, there's only one force on the 6. The 4 is dragging the 6 with it. Some force F. It's going to be equal and opposite to this one. Newton's third law says that force on 4 by 6 equals force on 6 by 4. And that's it. There's like gravity and normal, but these just cancel out. There's no more horizontal forces. This is frictionless. So I got that force F. I divide by what? 6. That's the mass of the 6. I multiply. Look at what I get. 12 newtons. They're the same because Newton's third law says force on 4 by 6 has to be equal and opposite to force on 6 by 4. I was just finding the magnitude here. I wasn't really worried. I threw in this negative. That took care of the sign there. So really they are equal and opposite. I just got the same value because I peeled off that negative and treated this as the absolute value of the force. All right, how does this get harder? I mean, they might throw some inclines at you over here. What if you got a block on an incline? Well, you got to remember that the component of gravity that goes down along the incline is always mg sine theta. And you can remember this because, like, it slides down the ramp. Sometimes people put mg cosine theta for this. But you got to remember, like, mg, that's the noise it makes as it slides down the ramp. So I got some 4. I'm going to treat g as 10. Because you can do that on the multiple choice, and I'm pretty sure for your response, they don't care. 4 times 10, sine of 30, well, that's just a half, so I get that the force down the ramp here is just 20 newtons. What about the normal force? If I wanted the normal force, that's also mg, but this one's cosine of theta, as long as you're talking about this theta right here of the ramp's angle with respect to the horizontal. So that's going to be 4 times 10 times cosine of 30. Cosine of 30 is root 3 over 2, so that's going to be like 40 over 2 times root 3. We can call that 20 root 3 newtons. Okay, what do we do with that? Well, what if they give you some coefficient of static, coefficient of kinetic? If you remember, the maximum force of static friction is always going to equal mu s Fn. This is the maximum force of static friction. This isn't the force of static friction. I'll show you what I mean. Let's say we just plugged in values. Mu s is root 3. Okay. And then mg cosine theta, we just said is 20 root 3 newtons. So this is going to be 20 root 3. This is going to be 3 times 20 is 60 newtons. That's not going to be if this question was posed like this and they said, what's the static frictional force? Don't be telling them 60 newtons. You kidding me? 60 newtons? You're telling me 60 newtons backward, 20 newtons forward? This box would slide up the ramp. It obviously doesn't slide up the ramp because static friction is just going to do the minimal amount it needs to do. So this is just how big it could be. But the value it's going to be right here, if this is not sliding, if it's at rest there, this is going to be 20. It only exerts the force back that it needs to. It could keep doing that until you get to 60. If I start pushing forward here, I could add another 40 newtons before this thing would budge. That's what this number tells you. So this mu SFN tells you the maximum static frictional force. Now, mu KFN, this is the kinetic friction. If you're sliding this is the amount of kinetic friction. So let's say this was root 3 over 4. That was our coefficient of kinetic friction. I multiply that by 20 root 3. I'm going to get 60 over 4. That's going to be 15 newtons. Okay, let's say I give this a little kick, like I just, boop, I give it a kick so it overcomes static friction. As it slides down the ramp, now you could be like, well, my acceleration parallel to the ramp, because Newton's second law works for every direction, even this parallel direction down the ramp. This is going to equal the force down the ramp, which is 20 newtons, minus my coefficient, or my kinetic friction, which is 15 newtons, back up the ramp, divided by my mass of 4, I would get 5/4 meters per second squared. Again, it wouldn't do this on its own because this maximum static friction force is bigger than this force down the ramp. But if you give it a little boop, so you force it to start sliding, then you can go into kinetic friction mode, find the acceleration. That would be the acceleration down the ramp. What's the acceleration perpendicular to the ramp? 0. This thing doesn't come flying off or going into the ramp. So the net force on a block, on a ramp, is always whatever the force is in the parallel direction. Okay, how's this get harder? Well, people don't like centripetal. They get confused by this. It's the same formula. It's still Newton's third law. It's just the acceleration we plug in is this, the centripetal acceleration, which is always directed into the circle, in toward the center of the circle. For any object going in a circle, your centripetal acceleration points into the circle. And this is, it turns out, is v squared over r. So you just take this, plug it into there, and suddenly you've got Newton's second law for a centripetal motion problem. What forces do I plug in? Only forces that are like into, radial. I'm going to put radial forces. Forces that are like into or out of the ramp. Into is going to be positive, out of is going to be negative. What if it's parallel? You don't put that in. You don't put any tangent forces in here. Only forces in toward the center of the circle or out. That's why I call them radial. So like down here, you'd have normal force on this car. You'd have gravity right here. How would you use this formula? You'd have something like v squared over r is going to be, all right, forces into are positive. So I got to put Fn minus mg divided by the mass, and then I could solve for what I want to solve for. How about up here? I got gravity straight down still. This time I have normal down. This force up here is down. Like this is force. Surfaces can only push. This can't pull. So the force from the roof here would be pushing down on the car. Now they're both positive, because you might be like, well, they're both negative because they're downward. No, they're both positive because they're inward toward the center of the circle. So I'd have Fn positive plus mg over m. What if the car's on the side of the wall? Now Fn points this way, gravity's down. I got some other force this way if I want. Maybe he's on the brakes or something. It doesn't matter. These tangential forces don't matter. All I'd have here is v squared over r would be forces into, that's still positive. Fn goes into over m, and that'd be my centripetal for that case. So be careful. Into forces are positive, out of forces are negative, and tangential forces don't get plugged in here, at least if you have v squared over r on the left-hand side. What if you got an orbits problem? Same issue. You're going to put v squared over r over here. It's going to equal the net force over the mass. It's just the force of gravity on an object, between planets and whatnot. The most general Newton's universal law of gravity is Fg is going to be big G, at least the magnitude of this force. Big G, mass of one of the objects, mass of the other object, Earth and Sun, divided by the distance between them squared. That's what you would plug into here. But you might be confused. You might be like, all right, fine, I'll do that. And mass of the Earth, mass of the Sun, distance squared. You might be like, but which mass is this? Is this mass down here the mass of the Earth or the mass of the Sun? Well, it depends. Do you want to find the velocity of the Earth or the velocity of the Sun? It's probably velocity of the Earth. I mean, the Sun ain't going nowhere. Earth's the one that's going to have the speed. Well, if this is the velocity of the Earth, then this is the acceleration of the Earth. This needs to be the force on the Earth, and that needs to be the mass of the Earth. So this needs to be mass of Earth. That means mass of Earth cancels, and the speed of Earth does not depend. It's kind of counterintuitive. Does not depend on the mass of the Earth. What it depends on is the mass of the Sun, because the mass of the Earth cancels out. And it's like, duh, yeah, because the mass of the Sun is what's like pulling this thing toward it. Change the mass of the Sun, you'll change the speed of the Earth. Change the mass of the Earth, you won't change the speed of the Earth. Everything out here, if you had another mini Earth, baby Earth, if it had the same, it would need the exact same speed the Earth does to orbit at this same radius. It wouldn't need any more or any less, because that speed of the Earth only depends on, be careful. This r is also d. That's the radius of the circle is also d. So I can cancel one of these, and you realize, oh, shoot, I can get the velocity of the Earth or anything at that radius. It's going to depend on g, universal constant, mass of the Sun, the thing it's orbiting, over the distance it's orbiting from the Sun, but does not depend on the mass of the orbiting object. Energy and work is cool. Lets you save some time sometimes. People get kind of confused. This is a big, nasty equation right here. It's like, what is this talking about? This is the work done by a force. Forces do work. How do they do work? They do work if there's a force over a distance. Like if you apply a force on something and it doesn't move, you're not doing any work. But if you apply a force on something and it does move, you will do work. You'll do work, and that work will, oh my goodness, this thing doesn't work. Yay. Okay. You'll do work, and that work will equal the integral of f dot dx. What is a dot product? Well, you can always rewrite this as magnitude of one of these times magnitude of the other times the cosine of the angle in between these two things. So this angle here is angle, Teddy wants to do some work. I know, buddy, I want to do work too. F times dx. So this is the angle between the force and the direction of motion. So consider gravity. Let's just make it real here. This is the force of gravity. It points down, obviously. If this ball also moves down, that's the direction of motion. These would be in the same direction. This theta would be 0. Cosine of 0 would be 1. That makes sense. This is how you do the most work. You want to do the most work, you push in the direction of motion. This would be positive work. What if I move this ball upward? If I move it upward, dx goes up, force is down. That's 180 degrees. So now this is 180 degrees. Cosine of 180 isn't 1, it's -1. You're doing negative work. Gravity, or sorry, if you were gravity, gravity's doing negative work. If this ball moves up and gravity's down, gravity would be doing negative work, trying to take away energy. If this ball moved horizontally, that'd be 90 degrees. Forces at 90 degrees don't do any work because cosine of 90 is just going to be 0. And so this is how you might be like, well, what the heck is this integral here for? Well, gravity's nice. Gravity just be staying the same the whole time. I could pull F out. I would just get the work done is the magnitude of the force times how far I went. Guess what? mgh is no surprise. That's the potential energy. But what if my force wasn't constant? Well, maybe my force is like a function of x. Maybe my force gets bigger and bigger or smaller. Then you just plug that force in here, integrate it. That gives you the total work done. You might be like, well, why do I care about work? You care about work because this number tells you how much change in energy. If something does work on something else, it's adding or taking away energy. If it did positive work, it adds energy. Do negative work, takes away energy. You might be like, well, why is this equal to negative delta U? Well, think about it. Let's say the mass goes down. We just said the work done would be positive, right? For gravity to be mg times how far it moved down. Okay, great. That's the change in energy of the ball. So you got to be careful. This over here is work done by gravity. This is force of gravity. This isn't change of energy of gravity. If you're doing work, you're giving that energy to someone else. The ball gained energy. What kind of energy? Gained kinetic energy. So the kinetic energy would be what's equal to mgh. This mgh turns into kinetic energy. Ball gained energy here. But that means gravity lost energy. Obviously, if a ball moves down, you have less mgh, less potential energy than you did before. That's why there's this negative here. If the ball gained 10 joules, joules is the unit of energy. If the ball gained 10 joules by falling downward, well then the change in potential energy, I move this negative over, the change in potential energy would be negative 10 joules because if a ball moves down, it gains kinetic. It only does that because it loses potential energy. And so another way to geographically, go on a map. Another way of geometrically thinking about this force integral is that if you get a force function as a function of position, well, the area here would be the work done. Why do you care about that? Because it's the change in energy. So it could let you figure out like, oh, how fast is the ball going? I can find that area. That's the work done. So it's probably like, maybe the object sped up. That's how this energy manifested. I can plug it into this formula that this area is 1/2 mv squared. One last thing on this. You might be like, dang, this guy likes talking about this. If you have work, the net work, i.e. work done by all the forces, it doesn't just equal any change in energy. It definitely equals the change in kinetic energy. That's it. You add up all the forces on an object, find the work done by all of it, that's change in kinetic energy. Work done by gravity might change your potential energy or your kinetic energy, who knows, spring energy, but net work by every force on an object has to change just the kinetic energy of that object. Okay, what if you had a spring? Well, it's kind of interesting because like the spring force, we know what the spring force is. It's like kx, or at least the magnitude of it. So say I plug that in up here. Okay, fine. Work done is integral kx dx. Well, shoot, guess what I get? I get 1/2 kx squared. It's no surprise that that's the formula for the potential energy from the spring. You might be like, why is it positive here? Well, this spring lost this energy. Like I really should have been plugging in a negative here or whatever. Lost this energy. If I want to find, if I want to get rid of this negative, this would just be, positive 1/2 kx squared. But that's how you get the formula for springs. And you can do kinetic, you can do conservation of energy just like normal on the AP Physics C exam. I started off with 1/2 kx squared. What did it turn into? Probably 1/2 mv squared. Energy will be conserved. This energy of the system will equal 0. The change will equal 0 if there's no external work. So as long as you put everything in your system, everything interacting, spring, box in my system, well, then you say, well, change in the total energy 0. In other words, the energy I had initially equals the energy I had finally. You just be setting potentials equal to kinetics or vice versa, and you can solve for what you want to solve for. You could also rearrange this work formula. Look at this. Work, we said, is integral. Let me write it this way. Let me write negative delta U is equal to integral f dot dx. And let me move that negative over. I don't want the negative here. I want the negative over here. Boom, there we go. Okay, think about what this is saying. This is saying, hey, you want to change in potential energy? Well, then add up a bunch of, that's what the integral means. Integral means add up a bunch of f dot dx's. Well, when you're like, well, what if I only have one little bit of f dot dx? If you only have a little bit of f dx, then that just changes this by an infinitesimal amount. You only change this u by a little amount if you're not adding up a bunch, just a little bit. You still have that negative. Now I rearrange this and now we get force is negative du dx. What does that mean? Well, if you had a potential energy graph, this means the slope of u as a function of x. The slope here, well, negative that slope would be the force on the object. So right here, I'd have a positive slope. That's a negative force. You might be like, that's weird. How can I think of that? Well, look, if I put a ball here, which way does it roll? Leftward, duh, negative direction. Well, right over here, look at my slope over here. I got a negative slope of my u. Negative slope of u times this negative out front. It's going to be a positive force. Yeah, because if I put a ball here, rolls in the positive, goes in the positive direction. So negative direction, positive direction. What if I put a ball right here? Well, there's no slope. Du dx is 0. That makes sense. How much force would I have making me go right there if I put a ball right there? None. This is an equilibrium position, and this is a stable equilibrium. So this is a point where the force is 0, and if I displace it a little to the right, it rolls back to the left. And if I displace it a little bit to the left, it rolls back to the right. It's stable equilibrium right here. This up here is unstable equilibrium. Look, the force is still 0. My slope is still 0 here. But if I displace my ball a little bit to the right, it's going to like cascade that way. And if I displace it a little to the left, cascade that way. This is like sitting on the head of a pencil. This isn't going to stay steady. Like if you did it perfectly, I guess so. But this is unstable equilibrium right here, even though the force is 0. This is stable equilibrium, force is 0. And that's kind of a quick way to figure out, oh, I put the ball here, it rolls downhill. Now, the ball's not going up and down. This is supposed to be like a 1D example. The ball's only going left and right. But you can kind of think, oh, ball rolls downhill, therefore ball goes rightward. Ball rolls downhill, therefore ball goes leftward. Ball's at a perfect position to have no force, so it just sits there. And you can check if this is right. Does this formula actually work? Well, this is the potential energy gravitationally, the universal law of gravitational potential energy. What if we took a derivative of it? And in fact, negative derivative. So this is the gravitational potential energy. Let's take a negative dd. Well, it wouldn't be x here. The relevant variables are, so ddr. Take a derivative of this. This negative cancels that negative. I take a derivative of this mess. I'm going to get g. That's a constant. m1, m2 over. Derivative of 1 over r would be negative 1 over r squared. And that is indeed the force of gravity would be negative this. You might be like, negative? I don't remember seeing that negative. But remember, big G, mm over r squared, gravitational force. The negative's there, it just says it's attractive. So if you see a negative force, it just means attractive force when it's a radial force like this. So the negative's always there. We usually just write this as absolute value, so we get rid of that negative. But there's technically a negative there because it's attractive. If there was a positive there, it would be repulsive. Okay, how about momentum and impulse? Momentum and impulse, like, dang, I want a cool formula like work and energy does. Well, I'll give you one. Here we go. Look at the momentum, which is defined to be mv, and it's a vector, so it has a direction. Unlike kinetic energy. Kinetic energy has no direction. It's a scalar, but momentum is a vector. Momentum rightward is different from momentum leftward. Momentum has a cool formula like work. Instead of work, though, it's impulse. Impulse is not the change in energy. It's the change in momentum, and it's equal to integral of f, not dx, but integral of f dt. So if you find the area under f dt, so if they give you, you got to look, what is this graph? You know what I mean? You got to check, is this x or t? If it's t, area here gives you the change in momentum. So in other words, like mv final minus mv initial. So that's useful. And we call that the impulse. The impulse is the change in momentum or integral f dt. What if f is constant? Well, then it's easy. Then it's just like f times delta t. You can pull that out of the integral. And you could rearrange this formula just like we did a minute ago. Instead of saying that delta p is integral f dt, rearrange it, you get that f is dp dt. What does this mean? Well, if you get a momentum graph, the slope of this momentum graph is the force. So in this case, the slope is positive. That means there's a force on this in the positive direction. It's not like ball rolling downhill anymore. That was potential energy. Up here, the slope is 0, so the force at that point would be 0, and so on. It's just there's no negative sign. Why do we care about momentum? Because if your system is closed, your momentum's conserved. In other words, you could just do momentum initial equals momentum final. This is why we liked energy as well. You could just say conservation of energy or conservation of momentum. Just remember, these are vectors, negative counts. So if I want to find the final speed of the masses, I could be like, okay, momentum's mv. So my initial momentum in the system is 6 times positive 3 plus 2 times negative 1. This thing is a vector. You got to treat it like a negative if it's negative. Equals, let's say they stick together. Okay, well then you have 6 plus 2 total mass times unknown v. I'd have 18 minus 2 is 16 equals 8 times v. My v final of this whole system would be 2 meters per second. What if I wanted to find the impulse? You're like, damn, I don't know what impulse means, but remember, impulse is the change of momentum or integral dt, but I don't need to do that. If I went on each mass, let's say I want to find the impulse on the 6, then I find the change of momentum on the 6. I'd say momentum final of the 6 minus momentum initial of just the 6, not the whole system, equals momentum final of the 6 would be 6 times final is 2 meters per second minus 6 times initial was 3. So I get 12 minus 18 is negative 6. And the units is going to be either Newton seconds or kilogram meters per second. What if we did this for the 2? Well, you'd do the same thing. You'd say impulse on the 2 would end up being positive 6. These are going to be equal and opposite due to Newton's third law. And that's why the momentum's conserved. If one of these gained momentum, the other lost momentum in the same amount, and you didn't change the momentum of the system unless there was an external force. Only external forces can change the momentum of the whole system. There was kinetic energy lost, though. These stuck together. How could you find that? You'd be like, well, what's my initial kinetic energy? 1/2 6 times 3 squared, 1/2 mv squared, plus 1/2 2 times, sure, you could write it as negative 1, but it's going to get squared, remember? So this isn't a vector, so it doesn't matter. Negatives kind of don't matter here. Just leave it off and it doesn't matter. Equals, okay, I get 3 times 9 is like 27. Plus, this is going to cancel here, plus 1 is like 28. That's my initial joules before the collision. What about after the collision? I'm going to have 1/2, total mass is 8, times 2 squared. Well, one of these cancel one of these. I'm going to have 16. I lost a lot. I lost 12 joules of energy in this collision. Okay, so that's energy in a collision. How about center of mass? Well, the center mass is the position where these masses would balance. Like say I connect them with a rod. I want to know where would I balance this thing? Well, obviously it's going to be closer to the heavier mass. In fact, if this mass is 3 times the mass of the other mass, then the center mass is 3 times closer to it. So you just be like, well, it's going to be like over here somewhere, so that if it's 1 away, then this one would be 3 away. How do I find the center of mass? I could just do, there's a formula for it. You could do x center mass is going to be m times, I got to choose a position. Let's call this x equals 0. It doesn't matter where you call it. You're just going to be measuring from this point. If I call that x equals 0, I'm going to do 6, one of the masses times its position is 0. So it's like mx1 plus the other one, 2 times its position, which is 16 meters away. Look at that. Divided by the total mass. So it's going to be 6 plus 2. So this formula for center mass is really x center mass is like m1 x1 plus m2 x2. You just keep going divided by the total mass. And what would I get here? I'd get 2 times 16 32 over 8 gives me 4 meters. It'd be, when you mean 4, like 4 meters, where from where? Well, from where you measured x equals 0, it'd be 4 meters. It'd be like right here, that's where you'd balance it. What's the speed of the center mass? It's the same formula. Look, if you want to find the speed of the center mass, look how easy this is. m1 v1 plus m2 v2. Just to replace these x's with v's, you still divide by the total mass, and that's the velocity of the center mass. So I could say 6 times 3 plus 2 times negative 1. I'm talking about velocities now. So I got to throw that negative in there. Divided by 6 plus 2, I get 18 minus 2 is 16 over 8. Oh my goodness, I get 2 meters per second. And you might be like, what? That looks familiar. Yeah, because look, this is just like the total momentum here. This would be what the speed is of the center mass after the collision. If they collide and stick together, they're still going to be moving 2 meters per second. We just found that a second ago. You're like, how come it didn't change? They collided. Yeah, only external forces can affect the speed of the center of mass. Force of 6 on 2 and force of 2 on 6 cannot affect the motion of their center of mass. Only external forces can affect this. So if this center of mass was moving with 2 meters per second before the collision, it's going to be moving with 2 meters per second after the collision, which is kind of cool. All right, angular kinematics is just like regular kinematics. We just got new characters. Instead of x, we call it theta. This is, instead of position, this is the angular position, like it's the angle you're at. Instead of v, the velocity, we call it the angular velocity. That's omega. Instead of a, the acceleration, this is angular acceleration, alpha. And their definitions are the same. Omega, the angular velocity, is derivative of the position, or angular position. And the angular acceleration is the derivative of the angular velocity. Theta typically has units of radians. That means omega's in units of radians per second. And that means alpha's in units of radians per second squared. And all the interpretations hold. Slope of theta gives you omega. Slope of omega gives you alpha. Area under alpha gives you change in omega. Area under omega gives you change in theta. So it's all the same thing. You know, if they give you one of these as a function of time, you can take an appropriate derivative or integral to find whichever other thing you want. And again, if the angular velocity is constant, it's easy. Well, the angle you go through is omega times time, just like distance equals rate times time. Angular distance equals angular rate times time. If your angular acceleration is constant, you get angular kinematic formulas. They look like these. They're just like the other ones. They're only true if angular acceleration is constant. If angular acceleration is not constant, well, you better be using conservation of energy, angular momentum, or just crafting your own angular version of Newton's second law, which looks like this. Instead of A, it's alpha. Instead of forces, it's torques. And instead of M, it's I. What are all these things? Well, I'll show you in just a minute. But first, let me be clear here. You can always relate these back. Let's say I know what angle I went through right here. Like this is the angle I went through. It looks like about 60 degrees or something like that. Well, let's say I didn't want to know the angle. I wanted to know how much distance I went through, how much arc length I went through. We usually call this S. S, if you remember, is going to be R, the radius times theta. As long as you're measuring this theta in radians, that's why we like radians. So the arc length is R times theta. Well, we know omega is d theta dt, but let's smuggle an R in here because watch. R theta, I just said, is the distance. So derivative of the distance with respect to time, I know that's just velocity. That means V, the velocity, is R omega. So R times omega is the speed, the regular speed, like meters per second speed, not like radians per second speed. So you can always take your angular variable, kinematic variable, multiply by an R, get your regular variable. So R times angular distance gives you regular distance. R times angular velocity gives you regular velocity. In fact, use this so often, you should memorize it. You know, V is rho omega. This is R times omega, looks like rho omega. Let's throw another R in here. Alpha is derivative of omega with respect to time. So let's smuggle an R on both sides. You know, I can multiply both sides by the same thing. I don't change it. But R omega, I just said, is V. But what is dV dt? Well, that's just A. So just like V equals rho omega, A equals ralpha. So I take R times my alpha. That gives me my acceleration, but specifically my tangential acceleration, not my centripetal acceleration. Centripetal acceleration points inward. We already know how to find that. Oh, thanks, Adobe. Giving me messages. Equals V squared over R. That's the centripetal acceleration. That's always inward. But the tangential acceleration is what you have if you're speeding up in your rotation. You know, if you do have an angular acceleration, which is what you'll have if your rate of change of omega is increasing, then you'll have tangential acceleration, and you can find it like this, R times alpha. Sometimes people get confused. They're like, wait. I've seen R omega elsewhere. When there's a ball rolling on the ground without slipping, if it's rolling without slipping, sometimes people use R omega to find the speed of the center mass of the ball, and that's true. So R omega does two things. You can use R omega to figure out, hey, what's the speed of a point on this rotating object about, relative to its axis that you're rotating about. And the further out you go, the bigger the R is, the faster this thing goes. So if you're on a whirly ride, the further out you go, the faster you'll be going. This thing's just rotating in place. But if you have this thing on the ground and it's rolling across the ground without slipping, now this R omega also, if you plug in the total R, the actual radius of the object, you multiply by the omega this thing's spinning at, you'll get the speed at which the center travels. So in other words, rho omega does two things. It tells you the speed of an object about the center, and if you're rolling without slipping, it tells you the V of the center. The center of mass will be moving with R omega as well. So that's important if you're rolling without slipping. So in this formula, Newton's second law for angular, alpha is net torque per rotational inertia. You might be like, what the heck is torque, dude? I don't know about torque. What does the formula get on the formula sheet for the AP Physics C exam? It's torque equals R cross F. Like, dang, what's a cross product? Well, you can just call the magnitude of any cross product. It's going to be equal to the magnitude of the first vector times the magnitude of the second vector times sine of the angle between the first vector and the second vector. So the magnitude of the torque, like don't be using a cross product. You can draw this big old determinant and whatnot for this thing. You don't need that. Maybe in college you need that or whatever, but often you can just get by with finding the magnitude and then direction separately. So I got the magnitude of R, magnitude of F, sine of the angle between R and F. What is R? What is F? Well, say you got some object, this rod here. You got 20 newtons exerted on it. Okay, there's my F. That's the force. What is R? R is sometimes called the lever arm or whatever. It's a point that goes from the axis, the point you're rotating about, goes from the axis all the way to where the force is applied. That's R. R goes from the axis to where the force is applied. And this theta right here is the angle between that R and that F. So it's not this one, that's bait. Don't be taking this bait. This 30 would be the angle between R and horizontal. I don't see horizontal in here, I see R and F. So you take R, you take F, you find the angle between those. This would be 60 degrees. So you'd have to do, okay, my torque for this force would be R. Well, it's not 10, it's not 4. R is going to be this length right here, which is 10 minus 4. So it'd be 6 meters. These are bait too, dude. The APB throwing out bait. 6 meters times 20 newtons, R times F, times sine of the angle between them, which would be sine of 60 degrees. That's how I get my torque. And you might be like, but by getting rid of the cross product, we don't know which direction it goes. Well, yeah, you do. Look, the force goes this way. Guess which? That goes counterclockwise. Like, duh. Finding direction's easy for these easy problems. You don't need to do the full cross product. This is a torque of 6 times 20 times sine 60. It's in the counterclockwise direction. That's what you'd plug in up here. You'd just call one of these positive. Typically, we call counterclockwise positive. If there were any torques going the other way, you just plug those in as negative up here in this numerator. So how do you find the I? There's this I in the bottom, right? Down here, like there's this I. How do you find this? Well, that's rotational inertia. That gives you an idea of how hard it is to rotate something. If you just have a point mass rotating about the center, it's not bad. Point masses have a rotational inertia. So if this M is orbiting, the whole mass is orbiting about some center R away, then the rotational inertia is just going to be M times R squared. Mr. Squared over here. What if you don't have that? What if this mass is like distributed, it's rotating here, and it's like a rod? Well, then you got to do an integral. Like, dang, how do I do this integral? They give you this formula, but what they don't give you is, well, I'll show you. You get integral R squared. You're like dm. So R is how far from the axis you're talking about. dm, you got to imagine like some infinitesimal m here. Physicists are simple. We're like, dang, dude, all I know is that rotational inertia for a point mass. Someone comes up like, hey, I got this rod here, and I'm like, oh, I'm going to make it into an infinite number of point masses. Here's a point mass. It's right there. It's infinitesimally thin. And it's exactly a distance R away. I'm like, ooh, okay. I know that this little piece of mass right here would have a I of dm, differentially small m, so this would be a differentially small I, times R squared. Okay, how do I find the total I? You integrate both sides. That's how I get this formula here. But you're like, what do I write as dm? Well, so you got to come up with this idea of lambda. Lambda is the mass per length. Specifically, it's like infinite. So imagine I take this infinitesimal mass right here. I divide by the infinitesimal length of this region. That gives me the mass per length right there. And that's dm per dl. That's lambda. It's kilograms per meter. This is how I find dm. I'm not going to ever leave this as dm, really. I'm going to write this dm as lambda dl. Okay, so I got lambda times dl. That's what you have to replace dm with. They don't give you this on the exam. You got to remember it. Equals, let's say my lambda is a constant, like I have uniform density throughout here. So I'm going to get lambda integral R squared dl. You're like, what do I, dl? But look, dl is the same direction as dr here. So it's like simple. They're the same direction. I can call them the same variable, dr. What do I integrate from? Well, the closest mass I have is 0 away. So I'm going to go from 0 here all the way to the length of this thing is L away. So I have lambda times integral R squared would be R cubed over 3, but evaluated between 0 and L. So I'm going to get lambda times L cubed over 3. And you're like, that's not what I remember the I of a rod being. Yeah, because look, lambda is the mass per length. So this lambda was uniform. So I can just write it as total mass per total length. So I know if it's uniform, then the little bit of mass over this little bit of length should be the same as the total mass over the total length. I know the total mass is m, total length is L, so let's plug that in. Mass per length is the lambda, L cubed over 3. This cancels one of those. I'm going to get I is 1 third ml squared. That is the rotational inertia of a rod about its end. You might be like, dang, but what if I had the rod rotate about its center? Okay, fine. Just integrate from like negative L over 2 to L over 2 because the furthest mass this way is going to be negative L over 2. The furthest mass this way is going to be L over 2. You'd get 1/12. You just integrate from wherever you want to wherever you want. These limits will give you the different factor out front here. And now you got it all together. You can know how to find the I. You know how to find the torque. You put it all together. That lets you figure out the angular acceleration. But these are hard. What if you have this like yo-yo? It's a cylinder, right? Let's say. And it hangs from a string. And if it falls down, it unwinds without slipping. Well, shoot. Okay, you got to draw your forces. So I got a force right here. Gravity pulls from the center, mg. I got another force right here, tension over here from the rope. That's it. Those are my two forces. So here's what rookies do. They're like, oh, dude, I'm a rookie. Look, I'm going to say, first of all, I'm going to do like T minus mg. Dude, rookie. I want a torque up here, not a force. These are forces, not torque. If you don't multiply by a F, multiply that F by an R, it's not a torque. So you got to multiply by R, first of all. And don't even call up positive, call down positive. It's going to be moving down positive. So we're going to call that the positive direction. So see, how much torque is there for this gravity? 0. Look at where R is. R is from the axis to where the force is applied. This force is applied at the center. R is from the center to the center. That's 0. This gravity applies no torque. Gravity doesn't cause things to rotate if you just throw them off a cliff. This tension will cause it to rotate. So this does exert a torque. I'm going to have tension T times R. R would be, right here, R. That's R. Angle between them is 90 degrees. That's nice. Sine of 90 is 1. And you're like, well, should I make this positive or negative? Well, I'm calling down positive. So you might think, oh, so let's call tension negative because it goes up. No. Look, we're not talking about whether this isn't tension plugged in here. This is the torque of tension. You might be like, what's the difference? Well, look, the torque of tension here causes this thing to rotate this ways. And if it rotates that ways, it's going to cause the thing to move downward, which is the direction we called positive. So torques that cause rotation, that move the object in the direction you call positive, you should just call positive. Otherwise, there'd be a relative negative sign you're going to have to deal with. They would give you the rotational inertia of the cylinder. You don't have to memorize these. You typically don't have to derive them either. 1/2 mr squared, the rotational inertia of the cylinder. And you're like, dang, okay, I can cancel that, but I got two unknowns. I don't know T. I don't know alpha. Yeah, so you're going to have to do one more formula. You're going to have to do A. The acceleration is net force per mass. Now we do plug forces in here. I'm going to call downward positive. These are actual forces. I don't have to multiply by R. mg goes down. Calling that positive. Minus tension goes up. Divided by m. You might be like, dang, but look, now I got A and I got alpha. But remember, A equals ralpha. So I could just, since A equals ralpha, that means alpha equals A over R. So I'm going to write this over here as A over R. I canceled one R, already. I'm going to cancel this R with that R, and I'm going to solve and get over here that T. If I solve this for T, move the 1/2 m over, T is going to be 1/2 ma. When I can plug that in right here, I'm going to move this m over. I'm going to get ma on the left equals mg minus 1/2 ma. I get to cancel all my m's. I'm going to move my 1/2 a over. I get 3/2 a equals g. That means that a is 2/3 g. Dang, these are hard problems, but they're not that bad. I mean, you got to remember to multiply by r. You got to remember to call the direction of motion positive and the direction of torque consistent with that motion positive. Otherwise, you had a negative all screwed up here. You got to remember A equals alpha. There are easy ways to do this. If you have kinetic energy, then if you think about this in terms of energy, it's a little easier. So an object rotating can have rotational kinetic energy. An object moving in a straight line can have translational kinetic energy. And an object that's moving in a straight line and rotating. So if the center of an object's moving and it's rotating about its center, then you have both regular translational kinetic energy and rotational kinetic energy. Why would you ever care about that? Because look how easy it is. Find the speed of this at this, say it's a cylinder again. 1/2 mr squared is the I of a cylinder. Find the speed of this at the bottom of the ramp. You use torques and you do that. You could do it. You saw all the mistakes you could possibly make though. Let's just do energy. E initial equals E final. Let's put everything in our system. The ball, the ramp, the earth. So what kind of energy does it start with? It starts with mgh. It has a mass m, let's say, equals. Well, it's going to end with 1/2 mv squared. It is moving. The center is moving, but it's also rotating. So I can't stop there. I have to do plus 1/2 I omega squared. Okay, so let's do mgh. We're going to plug in 1/2 mv squared plus 1/2. Be careful. This this is the I. The I of a cylinder, it turns out, is a half mr squared. So plug in whatever your relevant I is. This is a half. Notice there's two halves now. One half is normally there, and then one half smuggled in due to the I. Times omega squared, you're like, dang, but I got V and I got omega. I only want one of those, otherwise I have two variables. Yeah, remember, V is rho omega. That means omega equals V over R. Plug V over R into omega squared right here, and you'll get V squared over R squared, and something magical happens. R squared cancels R squared. M's all go away. We end up with GH is a half V squared plus 1/4 V squared, and a half plus a fourth is, what, 3/4? Is that right? V squared? That means V is going to be the root, if I solve this, of 4/3 GH. Boom, didn't have to do any torques. I just had to do conservation of energy. And you're like, but what if they asked me for acceleration of this object? Fine, just plug this into a kinematic formula. Call this your displacement. V initial 0. Kinematic formula related to the acceleration if you need to. All right, another way to, just like we had momentum, we could have angular momentum. Angular momentum is not mv. Angular momentum as a vector is r cross p. You're like, damn, cross product again? Yeah, but remember, you can find the magnitude by just doing magnitude of this one, magnitude of that one, sine of the angle between them. And we know what p is. P is just mv. So r times p is just mv times r. Remember, like, well, then why didn't you write it as rmv? Because I like writing it like this. Look, angular momentum is mrv. I like remembering this as Mr. V. Mr. V. And you might be like, where's the sine theta? Well, if r and v are at right angles, then sine of 90 would be 1. So if you just got a ball rotating in a circle, then that theta is all nice and 90 degrees. If it's not, that's fine. I mean, plug in the theta if you need to. So this would be like the angular momentum. Mr. V is the angular momentum of a ball, orbiting around some point. But what if the ball is orbiting around its center? Well, then the angular momentum is the rotational inertia of that thing times the omega that it's spinning with. So in other words, this I over here is mr squared. This I over here of a sphere, it turns out is like 2/5 mr squared. So if you're orbiting, you use Mr. V for your angular momentum. If you're spinning, you use I times omega for your angular momentum. You're like, but I don't care about angular momentum. Well, you should, because just like momentum has a cool formula and energy has a cool formula, angular momentum has a cool formula. Instead of work or impulse, it's angular impulse. Is there a letter for this? No, I just picked K. Why? I don't know, because J is impulse. So I just made K the angular impulse. K is the angular impulse. What is angular impulse? It's the change in angular momentum. How do you find it? Well, you can find the change in angular momentum, or you can integrate torque times time. Just like you can integrate force times time to get the change in momentum, integrate the torque times time, get the change in angular momentum. That means the area under a torque graph would give you the change in angular momentum, i.e., like I omega final minus I omega initial. And then these are your formulas for angular momentum. You could rearrange this formula if you want, and you'd be like, oh, dude, so the derivative of L with respect to time would be the torque. Yeah, just rearrange this. Just like derivative of momentum with respect to time gives you force, derivative of angular momentum with respect to time gives you the torque. You might be like, I don't buy it. I still don't care about angular momentum. Here's why you should care. If you put everything in your system, angular momentum is conserved. That means L initial equals L final. That means these problems get kind of easy. So if I put all this stuff in my system, then whatever the L initial is has to equal the L final. So say I had a cake down here spinning, right? I'm going to decorate it, and I just plop this cake right on top of it. This top one's not spinning, but the bottom one is initially spinning. So okay, L is I omega initial. So that's my initial. What is this going to be? Well, I of a cylinder is 1/2 m, and the m down here is 2m. So 1/2 2m times r squared times omega initial. And this top one wasn't spinning initially, so it has no angular momentum start. Equals, well, they say they stick together. These are cakes, so they stick together. They both start rotating with each other. This is on like a little spinner. Well, to end, I have some total I, right? I final times omega final, I initial, omega initial. I final is going to be 1/2. This bottom cake still has 2m r squared, 1/2 2m r squared, plus this top cake has rotational inertia, 1/2. Its mass is only m though, m times r squared. And then I multiply by omega final. Watch, r's cancel out, m's cancel out, 2's cancel out, 2's cancel out. I have omega initial equals 1 plus 1/2. This thing isn't 0, it's 1. Times omega final. This is 3/2. That means omega final is just going to be 2/3 omega initial. We got it without worrying about torque or anything like that. So conservation of angular momentum is pretty nice to figure out final speeds of things that are spinning. What if you had a point mass hitting a rod? Still do angular momentum. Watch, angular momentum initial equals angular momentum final. We want to figure out what the omega is afterward. This is a point mass though, so I'm not going to use I omega. I mean, I could if I wanted to be dumb, but I'm going to use Mr. V. M. This is going to hit at a point L away. So when it strikes, it's L away. Mr. V equals, this rod had no spinning to start with, no angular momentum. This ball bounced back. And so it bounces back, so it's going to be negative Mr. V. It's going the other way. This ball effectively has clockwise rotation to start, and afterward it's got like counterclockwise rotation, so negative Mr., but it's going half the speed because it lost some speed, V over 2, plus, so this is the angular momentum of the ball initially, angular momentum of the ball finally, plus I omega of the rod afterward. We can solve this for omega. We'd get omega is, what is this going to be, 3/2 ML over, we got a V over I. So that's my omega, and I can do it with conservation of angular momentum. You might be like, but I want to do I omega. Okay, do it. I want to do I omega for L. That's fine. I for a point mass is mr squared. Omega, remember, is omega, but watch a magic trick. Watch this. mr times omega, because r squared is r times r. R times omega is V. I still get Mr. V. It doesn't matter. You try to use I omega, you're forced to do Mr. V anyway, so it still works out. Okay, we're close. I got 2 more little slides here. Hooke's law is the force from a spring. Why is it negative? Well, because if you displace this to the right, the force is to the left. And if you displace it to the left, the force is to the right. The spring's a hater. It's going to try to do, again, it's going to work against whatever you do. That's why there's a negative here. This is going to cause this thing to simple harmonically oscillate. If I pull this back and let go, it's going to fly here, then it's going to fly there, and it's going to fly here. It's going to go back and forth forever if there's no friction or air resistance. And it would look like this. The position graph would look like the sine graph, and there'd be peak to peak. The peak to peak would be the period, and the period of a mass on a spring is 2 pi root m over k. How do you derive this formula? Well, use Newton's second law. We're going to do A is net force per mass. And I'm going to say the net force is negative kx over m. So I'm going to write this as a differential equation, but I don't want to write A as dv dt. This force isn't a function of v. This force is a function of x. So I'm going to write A as second derivative of x with respect to t squared, because if you remember, A is dv dt, but v itself is just dx dt. So I can write this as second derivative of x with respect to t squared equals negative k over m times x. And you can't separate this. So separate, integrate, celebrate doesn't work. I can't separate the bottom here of the second order differential equation. The way you solve this is you look at it, you go, oh, look at that. Look at that gorgeous graph. I remember this equation. If you have a second derivative of something equals negative a constant times that same thing, this is the formula for a simple harmonic oscillator. Think about what it's saying. It's saying, hey, can I think of a function that if I took 2 derivatives of it would equal negative a constant times that same function back? I can. That function would be x as a function of time would be some amplitude. This graph is cosine, so I'll just do cosine. It could have been sine though, of some omega, that's what we call this, times t. So, in math class, you might have called this b or something. Remember, omega is just 2 pi over the period, the time it takes to go through a full cycle. Let's see if this works. Let's take 2 derivatives of this. One derivative of this thing, one derivative of x would be, I pull out an omega, I'd get omega, chain rule, a omega, there'd be a negative from the cosine, so it'd be negative, not cosine, derivative of cosine is sine omega t. Let's take another derivative, 2 derivatives. It's going to be negative, I pull out another omega squared, a cosine omega t, and you're like, oh, look, 2 derivatives, that's what this is. Second derivative of x with respect to t squared equals negative some constant times this whole thing here is what we called x. That is x. So this is times x. So you're like, oh, dude, that does work here as long as omega squared equals k over m. Or in other words, since omega is 2 pi over t, this would have to equal, so I'm just going to call this omega is root k over m. That's what would go right here, root k over m. That should equal 2 pi over the period. In other words, The period, if I solve here, would be 2 pi 1 over root k over m, or root m over k. That's how you get. It's not fun, not pretty, but that's how you get the period. You derive the period formula for a mass on a spring. What if you had a pendulum? Last one, we made it, last slide here. What if you had a pendulum? Well, this isn't from force, this is from torque. So I say, well, I got a torque here. Gravity's that way. Here's my pivot right here. Gravity's that way, tension is this way. I ask myself, what's exerting torque here? Not the tension, because look, R goes from the pivot to where the force is. That angle would be, remember, torque is RF sine theta. And theta is between R and F. So R goes that way, torque goes back up. That's 180 for the tension, and sine of 180 is 0. The tension exerts no torque, but the gravity would exert a torque. So if I imagine continuing my R out, angle between R and F would be this same angle right here. So this would be this same angle right there. Why do I care about any of that? Well, look, because I want to do alpha is net torque over I. This is also going to be a simple harmonic oscillator as long as the angle's small. I'll show you why in a minute. And so, you're like, I know what to do. Instead of writing alpha as d omega dt, I'm going to write it as second derivative of theta with respect to t squared. Yup. Equals, the only torque in here is gravity. It's going to be force times r, which is the full length of this rod, times sine of the angle between them. And that angle here would be this angle there. If you don't like that, you can think about it like, oh, look, a supplementary angle, but sine of supplementary angles are the same value, so it doesn't matter. It's going to be the same thing. But I do have to throw a negative sign. There's got to be a negative here, just like negative kx. This is negative because, look, this is displaced in the positive theta direction, but my torque's trying to bring it the opposite way. So my torque's acting opposite the direction of the angular displacement. I divide by I. The I of a point mass is mr squared, because I'm orbiting about this point right here. And look, I get to cancel m. The mass of a pendulum cancels out. I cancel L, I cancel 1L. I get second derivative of theta with respect to t squared is going to be negative g over L sine theta. You're like, wait, so we're going to solve this by looking at it. We look at it, we go, ooh, look at that. And then you're like, huh? That's not a simple harmonic oscillator equation. The simple harmonic oscillator equation is second derivative of some function equals negative a constant times that function, not times sine of that function. Okay, here's where we get a little sketchy here. Physicists go, well, but hold on. They say if theta is small, and this is true, for small theta, sine theta is approximately theta. If you don't believe me, plug it in. Like try plugging in, and make sure you're in radians. Try plugging in sine of like 0.01, and you're going to get like 0.00999, which is basically 0.01. It's off by like a smidgen. So if theta is small, we pull a fast one. We go, oh, this is kind of equal to theta, and it's pretty close. So the pendulum is only approximately a simple harmonic oscillator. It will not be a perfect sine function. It'll be close. And it's close enough that it doesn't make much difference. And if your instruments in the lab don't measure to that decimal place, then it doesn't actually matter anyway. So we say, okay, this is fine. This is basically a simple harmonic oscillator for small angles. And I can play the same game. I say that this over here has to be omega squared, has to be g over L. And remember, omega is always 2 pi over the period. And therefore, I could be like, well, then omega is just root of this. That is equal to 2 pi over the period. That means the period is going to be 2 pi root, flip this whole thing, L over G. And that's the period of a pendulum. And if you don't like that, you're like, what? Physics is dumb, dude. Why are they making approximations? Fine, let me show you one that's not an approximation. It's called the torsion pendulum. Say you got something on a string and you just like, you rotate it, right? You twist the string, you let go. For a lot of cases, this torque will just be negative beta, some constant, times how much angle you moved it through. Not sine of the angle, just angle. So if I double the twist, I'll get double the torque trying to restore it. For this case, let me make some room here. For this case, you could be like, all right, fine. Second derivative of theta with respect to t squared equals negative beta, theta over beta. Negative beta theta over what? What are we looking at? I, the I of this thing. So we're doing torque over I. So we do negative beta over I times theta. And now you look at this, you're like, that's a good looking simple harmonic oscillator equation right there. It's second derivative of theta equals some constant times theta. And you're like, okay, I know how to play this game. This beta over I right here has to equal omega squared. That means the root of this thing has to equal 2 pi over the period. And that means for this torsion pendulum, the period would be 2 pi times the root of, I guess, whatever the I is, divided by whatever the beta was. And that's how you would figure out the period of some torsion pendulum. Okay, those were all the topics, pretty much all the topics from the AP Physics C mechanics exam. Good luck.